Hi everyone. In this video, we'll explore some connections between the Riemann and Riemann-Stieltjes integrals, in particular looking at two theorems, one of which shows a nearly identical theorem holding for Riemann-Stieltjes integrals that held for Riemann integrals, and another theorem which connects the two, which in particular allows you to calculate the value of a Riemann-Stieltjes integral using information about an appropriate Riemann integral. So the first theorem we want to look at today, again, is a theorem for Riemann-Stieltjes integrals, which looks very similar to a theorem we had for Riemann integrals. So the theorem says function f is Riemann-Stieltjes integrable with respect to alpha on the closed interval ab, if and only if, for every epsilon greater than 0, there is a partition P such that the upper Darboux-Stieltjes sum of f with respect to alpha minus the lower Darboux-Stieltjes sum of f with respect to alpha is less than epsilon. So if you recall, we had a similar theorem where we just replace Riemann-Stieltjes integrable with Riemann integrable. Of course, then we don't have an alpha. And in that case, we just had an upper Darboux sum of f minus a lower Darboux sum of f is less than epsilon. So the entire idea of this theorem is that the function is, in this case, Riemann-Stieltjes integrable if I can find some partition so that the upper and lower Darboux-Stieltjes sums are as close as I would like, right? So for any epsilon, I should be able to make this difference between the upper and lower Darboux-Stieltjes sums over that partition arbitrarily small, less than that epsilon. Now, we're not going to go through the proof of this. Really, the reason we're not going to go through the proof here is that the proof is nearly identical to the proof we did that a function f is Riemann integrable on AB, if and only if for every epsilon there exists a partition such that the upper Darboux sum minus the lower Darboux sum is less than epsilon. So this theorem is again, nearly identical. And one of the things I may have you do for homework, actually, is to go through and prove this using what we've already done for Riemann sums. Now, it's worth noting here, again, it's now that we know this theorem, the theorem for Riemann sums, or for upper and lower Darboux sums for Riemann integrability, follows as a special case of this theorem. So this is, in fact, a more general theorem. But the vast majority of the idea comes out of the proof that we did in the specific case where we were looking at Riemann integration. So again, once you have established this theorem, if you just take alpha of x to be x, then you can recover the same theorem for Riemann integration. This really is a more general theorem, but the special case of just proving it for Riemann integration gives you most of the idea. So what we want to spend most of our time on today then is looking at another theorem that connects Riemann and Riemann-Stieltjes integration. So this theorem says if alpha is differentiable, and of course when we're talking about Riemann-Stieltjes integration, we're always assuming that alpha is monotone increasing. So if alpha is differentiable and monotone increasing on AB, and both alpha prime and f are Riemann integrable on the closed interval AB, then f is Riemann-Stieltjes integrable with respect to alpha, and this is the most important part, we get here that the Riemann-Stieltjes integral over the interval AB of f d alpha is equal to the Riemann integral from a to b of f of x times alpha prime of x dx. So there's sort of a couple of things going on here. If we just assume that f and alpha prime are Riemann integrable, then we know that f is Riemann-Stieltjes integrable with respect to alpha. So again, this gives us a way of using information about the Riemann integrability of f and, well, not alpha, but something to do with alpha. So looking at Riemann integrability of things to do with f and alpha, and using those to conclude that f is in fact Riemann-Stieltjes integrable with respect to alpha. And then furthermore, what this equation does is it tells me how to compute the integral of f d alpha by computing a Riemann integral of f times alpha prime. So again, what it does here is it relates the Riemann-Stieltjes integral over here to a specific Riemann integral over here. Now, why is that valuable? Well, I mean, if you took Calc 2, you took a whole class in computing Riemann integrals, right? You've computed almost no Riemann-Stieltjes integrals. So this is a really nice theorem to have because it allows you to compute a Riemann-Stieltjes integral in terms of just computing a Riemann integral. Now, it's worth noting that this requirement that alpha is differentiable is a very strong requirement. You could sort of think, right, in general, to talk about Riemann-Stieltjes integrability, you just need an alpha that's monotone. If you took the set of all monotone functions alpha, right, and put them in a hat and pulled one out at random and sort of ask, I wonder what the probability is that I got one that's differentiable. Like the answer is zero, essentially, right? They're so rare that we would just say the probability is zero. So on the one hand, it's very unlikely that if you just encountered a Riemann-Stieltjes integral at random in the wild, that you would even be able to apply this theorem. On the other hand, right, a lot of functions we tend to work with are nice functions, right? Especially if we're going to compute things by hand. So if we're going to compute something by hand, maybe it's not so wild to assume that alpha is differentiable, right? It turns out you can, in some very specific cases, actually weaken this slightly to require not differentiability, but a special kind of continuity. But for our sake here, we're just going to assume differentiability. You actually still need more than just continuity to make this work. The other thing to mention here, right, is that you are swapping out, right, this for an integral of a product, right? So just sort of when you think about setting up or creating examples for this, you do have to be a little careful because you are going to have to integrate this product here. And this product may not necessarily be an easy thing to integrate by hand, right? However, if we sort of think back to the theory of things, if, say, alpha is continuously differentiable, now again, that's even a little bit more than is required, but if it's continuously differentiable, right, then at least from a theoretical perspective, this is going to be a continuous function. If f is also a continuous function, right, I'm going to have no problem with integrability here, right? And again, we know this will be Riemann integrable because it's a product of Riemann integrable functions on this closed interval, bounded Riemann integrable functions. So let's first see. So our main goal for this video moving forward is going to be to prove this theorem. But before we prove this theorem, let's first just look at a quick example, to see how this works. So imagine that I gave you, I said, let f be this function x cubed plus 1, let alpha of x be x squared, and I want to find the Riemann-Stieltjes integral of f d alpha over the interval 0, 1. Right? So my new theorem, right, tells me that this is precisely the integral from 0 to 1 of f times alpha prime. So if my alpha of x is x squared, this is going to be 2x. And now I can just compute this as a Riemann integral. So this is just what the integral from 0 to 1 of 2x to the fourth plus 2x dx. And now if I look at this, this will be, so take an antiderivative, this is 2x to the fifth over 5 plus x squared. Evaluated at 1 and 0 and take a difference. Evaluated at 1, I get 2/5 plus 1. Evaluated at 0, I get 0 plus 0. And so what I end up with here is just 7/5. So again, in the special case where, and again, this satisfies all our hypotheses, right? So just to reemphasize, right? This function alpha is differentiable. Its derivative alpha prime is 2x, which is continuous, so I know it's Riemann integrable. F of x is again continuous, so I know it's Riemann integrable. Okay, so f and alpha prime are both Riemann integrable, and therefore I can compute this as the Riemann integral from 0 to 1 of f times alpha prime. Okay, So again, very handy if I want to calculate these things by hand. Now, we want to think about proving this. Okay. And the proof is, I actually have a special note written in my book that this proof always, when I taught this class in person, it always takes me longer than I think. And in part because we're going to have to balance along the way sort of some really fine details. Okay. So what I encourage you to do as we get ready to prove this and as we talk through this proof is to take the time to first try to understand the high level structure of the proof. And we're going to start by outlining the proof. So try to understand sort of the high level outline of what's going on. Even once you have all the details written out, can I sort of make sense of, okay, here's what I'm doing in this chunk, here's what I'm doing in this chunk, here's what I'm doing in this chunk. And then once you feel like you have a good grasp of that, then try to go through and make sure you understand sort of line by line, where is each piece of this taking me? All right, so as we think about this, so just for our reference, here's the theorem restated again. Okay, and let me sort of give you an outline of the proof. This is how we're going to sort of break it down over the next several minutes. So the idea is going to be, if I look at this, I get to assume that alpha is differentiable, that alpha prime and f are both Riemann integrable, and then I want to show that f is Riemann-Stieltjes integrable with respect to alpha and that this equation holds. Okay. Now, the first thing I'm going to do, I need to make use of that integrability. So one way to think about this is I've got all of these things I get to assume about Riemann integrability. I've got to turn that into something about Riemann-Stieltjes integrability. So let me start by simply sort of, writing down what one of these means. And in fact, I'm going to use the definition of Riemann integrability, or I should say one of the characterizations of that, to pick a nice partition to work on. Okay, and we'll see why sort of that's the right partition. Okay, but I'm going to pick a particular partition to work on. Now, at some point, what I essentially have to do is I need to relate this dx and this d alpha. And the way I'm actually going to do that is I'm going to use the mean value theorem. I'm going to apply the mean value theorem to alpha on subintervals of my partition. That's essentially going to give me some relationship between, one way to think of it is we're going to sort of show that this d alpha is equal to alpha prime dx. Now, we're going to do that in the delta terms. So we're actually going to show that delta alpha k is equal to alpha prime of some value times delta x sub k. So we're gonna work in that context, but really what we're doing there is sort of showing this equivalence. But then, of course, we're doing all of this work here in terms of sums in 1 and 2. And so then in step 3, the idea becomes, okay, I need to somehow get away from these sums and back to integrals. So I have to sort of do some limiting type arguments to make my way back to, okay, these things hold for sums. Now, how can I make it true for integrals as well? Okay, so that's sort of the big picture idea. We're going to take each of these step by step as we work through the proof. All right, so let's start with the first. We need to sort of choose the right partition P using the Riemann integrability of alpha. Okay, so by the way, let me also say, in the book, this is just sort of presented all as one big long narrative proof, and that really is the way that the proof would go. I'm just using these steps as sort of intermediate thoughts to help us think about what we're actually doing in this proof. Okay, so right, the proof would start. I'm gonna take an epsilon greater than 0. And for reasons that will become apparent later, I'm going to choose a capital M, which is just going to be some positive real number, which is going to be a bound for my function f, such that so I'm just choosing capital M to be some real number that's greater than or equal to the absolute value of f of x for all x in the interval AB. Now, again, anytime I say choose something that satisfies these properties, you should say, how do you know you can choose such a thing? I know that my function f is Riemann integrable, so it must be bounded, right? So I know this is bounded. I'm just saying let m be some bound for the function f. You could choose it to be the least upper bound if you wanted to, but we don't need that. We just need some upper bound for the function absolute value of f. Okay. Okay. Now we want to use the fact that alpha prime is Riemann integrable. So since alpha prime is Riemann integrable, I want to use that sort of alternate characterization of integrability. So since alpha prime is Riemann integrable, there exists a partition P of of AB such that I can make the upper and lower sums as close as I would like. So such that the upper, now again, this is an upper Darboux sum, right? Because I'm doing here, this is the Riemann integral of alpha prime. So the upper Darboux sum minus the lower Darboux sum of alpha prime over that same partition can be made as small as I would like. Now, this is a place where if we were going to write the proof all on one screen, I would probably just put a box here and say, we'll figure out how small we need it to be later. We're going to have to erase several times over the course of this proof. So I'm going to go ahead and tell you what goes here. But if you're writing notes, what I might encourage you to do is just draw a box. We actually at this point have no way of knowing what the right value to put here is that's going to make the rest of our proof work. Okay, so I know because I've already worked out the proof, but if you haven't already worked out the proof, you have no idea how small you might need to make this difference. Okay, and the nice thing is, by that characterization of Riemann integrability, you can make this difference as small as you would like. So you could just put epsilon here, but maybe you need epsilon over 2 or epsilon over 5 or epsilon over 17, or maybe it has something to do with this m up here, right? And so in fact it does. So if you're working this on your own, you might put a box here and then come back and figure out what it is. I'm going to go ahead and tell you, though, what we're going to need is going to be epsilon divided by that capital M. Okay, so I can choose a partition such that these two are as close as I would like. I want to make sure that whatever partition I choose is always less than epsilon over M. Okay, that difference is always less than epsilon over M. All right, great. Now, what are we going to do with that, with this partition now? Okay, so this is sort of, this first step has been, let's find let's set up a partition using the Riemann integrability condition on alpha prime. Now, again, so far, all of this setup is a little bit mysterious, right? Because I've chosen a partition so that this property is satisfied. No idea why I need this number here, okay? Again, we're going to see that in a bit. Okay, so this is our step one. Step one, we're just setting up the appropriate partition. Again, this all seems a little mysterious until we get a little further in the proof. Like, why are these the things that I want? Okay. But now I do have a partition. Okay, and so now that I have a partition, I can start messing around with some other things. Right? I have some points to work with. Okay, so in the next step, we want to apply the mean value theorem to alpha on subintervals of the partition. Okay, so now what I want to do is I want to say, well, by the mean value theorem, we can choose, so I'm going to choose some points that I'm going to call TK. Okay, these points TK are going to go from K equals 1 up to N. Okay, such that, okay, well, I'm going to choose TK is going to be a point in the subinterval x sub k minus 1 x sub k. So each of these points comes from one of the subintervals of the partition. Okay, And this is where I don't need the mean value theorem for this, right? Um, but what I need the mean value theorem for is I want to choose them such that uh, delta alpha k, which is, if you just remember, that's just defined to be alpha of x sub k minus alpha of x sub k minus 1. If I apply the mean value theorem, I should be able to choose these so that tk is the point such that alpha prime of tk times x sub k minus x sub k minus 1. This is the mean value theorem here, although I've sort of rewritten it in an alternate form. Okay. I've multiplied over by the x sub k minus x sub k minus 1. But I'm really choosing tk in this interval such that this holds. So the mean value theorem is giving us this equality. And if I look at this, this is really alpha prime of tk times delta xk. Okay. So here, right, if I look at this, again, if you're having a hard time seeing this, this is really using the fact that the mean value theorem allows me to choose tk such that alpha prime of tk is equal to the average rate of change of alpha over x sub k minus 1 to x sub k. So again, that's normally how we might have written this mean value theorem, but I've just multiplied both sides here to get this. So again, that's the piece coming from the mean value theorem. Okay. Um, Now, I want to do a little bit. We've applied the mean value theorem here. Let's see how that's going to sort of percolate through this proof a bit before we switch to the next piece. So, since we chose our upper Darboux sum for alpha prime over the partition P minus the lower Darboux sum of alpha prime over the partition P. We chose our partition P so that this was less than epsilon over m. Then if we choose, so I'm going to choose some other set of tag points. So you can think of these T sub k's, these are like tags, right, of the partition, right? Because there's a tk in between each of the points of my partition. So I'm going to choose another set of tag points. So if we choose any other set of tags, and I'm going to call those sk, or again, sk should be in x sub k minus 1 to x sub k, then, well, if I look at this piece here, right, this is the difference. One way to sort of think about your upper Darboux sum, right, is that it's sort of the largest possible Riemann sum. And this is like the smallest possible Riemann sum. And so if the difference between these is less than epsilon over m, then if I take a difference between the Riemann sum if I look at these are really just two Riemann sums for alpha prime. Right? This is just a Riemann sum using the tags sk. This is a Riemann sum using the tags tk. The difference between these two must be less than the difference between the upper and the lower, because the upper and the lower give you the extremes, right? Any two Riemann sums must be below the upper and above the lower, so their difference must be smaller than the difference between the upper and the lower. So if I take this, which, by the way, I can do a little algebra on here. So what I'm going to do first is combine these sums. So this will be So if I just look inside first, right? Forget about the absolute values for a second. We'll come back to those. So if I look at each of these, I can see that I can combine the sums. They're indexed over the same range. And then I can factor out a delta xk. So I'll get a alpha prime sk minus alpha prime tk times delta xk. Now I have these absolute values, okay? But I could push them inside. Now, if I push absolute values inside a sum, you might normally think triangle inequality, which is smart. And you could apply triangle inequality here, but that would actually cause you a problem. If you will notice, all of the stuff, so this term right here is positive. Okay. And if I look at these terms right here, right, these are either going to be positive or negative depending on the right, exactly where we are in the subinterval. So I can apply this and just bring these terms here. Okay, bring the absolute values here. And now I have that this whole thing is less than epsilon over m. All right. So again, what this has done is shown us we picked our partition so that the difference between the upper and the lower sum for alpha prime over the partition was less than epsilon over m. Now what we've shown is for any tags sk and these very particular tags tk, that we can make the difference between those two Riemann sums less than epsilon over m. Okay. So now let's see how we can use all of this to get to what we want. All right. So now in the last step, we want to sort of formally establish the equality of the upper and lower integrals. But the way we're going to do that is we're going to sort of establish equality of sort of some Riemann sums or almost equality, then get to equality of some or almost equality of some upper and lower Darboux sums, and then get to upper and lower integrals. So we're gonna work our way sort of step by step through this. Okay. So by our choice of the points T sub k, remember these are the ones basically chosen via the mean value theorem. We see that if I look at this sum, remember these TKs were chosen so that this delta alpha k is equal to alpha prime of TK times delta xk. So just by the exact way we chose these in the previous slide, this is f of sk alpha prime of tk times delta xk. Now notice if we just stop right here and look at this for a second, what does this look like? This looks like a Riemann-Stieltjes. This is a Riemann-Stieltjes sum for f with respect to alpha. This is almost, but not quite, a Riemann sum for f times alpha prime. Why is it not a Riemann sum? If it was a Riemann sum for f times alpha prime, these would both be evaluated at sk. Or both at tk, actually. It could still be a Riemann sum just with a different set of tags. But this is not a Riemann sum with any set of tags because you're using two different tag points for each part of the thing that you're supposedly integrating. And you can't do that and have it be a Riemann sum. But this is where we sort of go, it feels like Feels like we're really close though, right? So we need to do a little bit of analysis to say, okay, well, maybe that's not quite right, but it's close enough. Okay, so let's see what we can do. Um, so now what I want to do, so hence, let's look at the difference between this thing. Okay, and I'm for the time being, all these sums are k equals 1 to n. I'm just going to drop off that notation for the time being. Let me look at the difference between this and the actual thing I would want. So if I look at this, this is in fact a Riemann sum. So here, this is in fact a Riemann sum for f times alpha. This is a Riemann-Stieltjes sum for f with respect to alpha. So what I really want to do is I want to show I can make these as close as I would like so that essentially they have to be equal. If I can make them arbitrarily close together, then their difference has to be sort of zero in some sort of limit, right? All right, which we'll have to also deal with. But let's see if I can make these arbitrarily close to begin with. So if I use my previous step here, so I'm just going to substitute this in here. Okay, so then this will be equal to the sum f of sk alpha prime of tk delta xk minus the sum f of sk alpha prime of sk delta xk. And now I see here, I can combine these sums. Both have an f of sk, both have a delta xk. The only place there's really a difference here is this alpha prime, right? This is alpha prime of tk, this is alpha prime of sk. And so if I collect all those things together, I get here, this is the absolute value of the sum k equals 1 to n. I'll introduce this back here now, f of sk. This would be alpha prime of tk minus alpha prime of sk times delta xk. All right. Now, I wonder sort of how bad can this be? I mean, again, I'd like to get these arbitrarily close together, like within an epsilon of one another. Okay, so how bad could this be? Well, let's start by doing a really rough approximation first and say, well, what's the worst f of sk could be? Well, in the very first line of the proof, we said, let's assume f is bounded by the absolute value of, let's assume the absolute value of f is bounded by m. So if we were to take this and apply the triangle inequality, so we could break this up and we get an absolute value of f of sk times an absolute value of alpha prime of tk minus alpha prime of sk. And then we get an absolute value of delta xk, but delta xk is always positive, so we can drop the absolute values off of there. And now the worst this thing could possibly be is m. Okay, and m is a constant, so I can pull it outside of the sum. Okay. And so now I get this, but now if you go back, remember we chose that partition of AB so that this difference here, right? One of the things we showed is by choosing our partition in that way, this difference would be less than epsilon over m. So this is strictly less than, I still have this m hanging out here, and this piece is less than epsilon over m. And so I get that this whole quantity is less than m times epsilon over m, which of course is just epsilon. All right. So now I've done a bunch of work here, but what have I really shown? Now, again, let's annotate some of this here to help us out. What is this really? This is really a Riemann, this term sitting here is really a Riemann-Stieltjes sum over the partition P with tags SK. But remember, the set of tags SK was just any set of tags. Okay. So any Riemann sum over the partition P, sorry, Riemann-Stieltjes sum over the partition P of F with respect to alpha. This sitting here is a Riemann sum of over the partition P of F times alpha prime. Okay. So what we've really done is we've shown that for any set of tags, right, because these SK were just arbitrary tags. So for any set of tags, the Riemann-Stieltjes sum of F with respect to alpha over this partition and the Riemann sum of F times alpha prime over this partition, I can make those as close as I would like together just by choosing the partition in the right way. If I choose the partition in the right way, it doesn't matter how I choose the tags. The Riemann-Stieltjes sum of F with respect to alpha and the Riemann sum of F times alpha prime will be within epsilon of one another. Okay. So now how do we pass then from that to showing that the actual integrals are equal? Okay. Because right now it feels like we've almost got the sums are equal to each other. Now we just need to get, we don't actually have their equal, we have their we can make them arbitrarily close. How do we get from there to equality of the integrals? All right. So now note that since, so what we had there was the Riemann sum over the partition P, sorry, the Riemann-Stieltjes sum over the partition P of F with respect to alpha minus the Riemann sum over the partition P of F times alpha prime can be made less than epsilon for any tags SK of the partition P, right? Didn't matter what those tags were. The SKs were just an arbitrary set of tags. All right, so note that since that is true, if I just break this up, okay, then we have two things. So we have that the Riemann sum, the Riemann-Stieltjes sum is less than the Riemann sum for F times alpha prime plus epsilon. So if this quantity happens to be positive, you could just drop the absolute values, move this term over, you get this. And if this quantity happens to be negative inside, then just the absolute value would be just flip the order, and then you would move this over, so you would get that the Riemann sum of F times alpha prime is less than the Riemann-Stieltjes sum of F with respect to alpha plus epsilon. All right. Now again, this works for any set of tags. Okay, for any set of tags, this holds and this holds. Well, if we think about expressing these in terms of their sums, right? So again, this is just the sum. This is the Riemann-Stieltjes sum. So this is just f of sk delta alpha k is less than sum f of sk alpha prime of sk delta xk plus epsilon. And this piece is just sum f of sk alpha prime of sk delta xk is less than sum f of sk delta alpha k plus epsilon. All right, now what does this give us? So we're going to keep sort of unfolding this layer by layer. Now imagine that I take a supremum of each piece of this, right? So I sort of ask myself, well, what's the worst this could be? Well, this is always bounded above by this. So taking the supremum of both sides, right? I'll still get the supremum of this is less than or equal to the supremum of this. And same thing over here. And so now, let's switch to a different color. So taking supremum or suprema of each side, this gives us that the upper sum, so this is the upper Darboux-Stieltjes sum of this, because this is a Riemann-Stieltjes sum, okay, is less than or equal to. Again, when you pass the limits, strict equalities can become equal. So this is less than or equal to the upper Darboux sum of f times alpha plus epsilon. And similarly over here, you get that the upper, this is the upper Darboux sum of f times alpha prime is less than the upper Darboux-Stieltjes sum of f with respect to alpha plus epsilon. All right, now if I recombine these, okay, I'm sort of going to now take this back to something that looks like this. And so hence, combining these two inequalities, basically if I subtract this over and subtract, oh sorry, this should be less than or equal to. If I subtract this over and subtract this over, I can basically again get that the absolute value of the upper sum of the upper Darboux-Stieltjes sum of P f alpha minus the upper Darboux sum of P f times alpha prime is less than or equal to epsilon. Okay. Now, this holds not only for P, but any refinement of P, right? Because as I take refinements of P, right, this this difference will get smaller and smaller. Okay. And so therefore, well, what happens if I take this for like finer and finer things, as I think about taking the infimum of all these upper Darboux-Stieltjes sums, I'm going to end up with an upper Riemann-Stieltjes integral of f d alpha minus here, as I take, again, smaller and smaller and smaller values. So I sort of think about taking infimums. I'm thinking about taking an infimum of these things. This will give me an upper Riemann integral of f times alpha prime. And now since epsilon was arbitrary, the only way this is less than or equal to epsilon for every epsilon greater than 0 is if this quantity is 0. Hence, since epsilon greater than 0 was arbitrary, we get that the upper Riemann-Stieltjes integral is equal to the upper of f with respect to alpha is equal to the upper Riemann integral of f times alpha prime. All right. Now, imagine I took all of this and repeated it, but sort of in the places where I took maxima, I took min or imps, I switched to sups, and sups, I switched to imps, right? Then I would get all the same things, but for lower sums and lower integrals. Okay, so I'll just say similarly, we can show that the lower Riemann-Stieltjes integral of f d alpha is equal to the lower Riemann integral of f times alpha prime. Okay, now we've now shown that sort of the thing holds for, so we started with sort of this works for Riemann sums, it works for upper sums, it works for lower sums. Now it works for upper integrals, it works for lower integrals. Now, how do I get to just the integral piece? Remember, I also need the upper and lower integrals are equal to each other, right? So now I've sort of got the right upper integrals are equal to each other and the right lower integrals are equal to each other. Now I need all of these to be equal to each other, but I know that this integral and this integral must be equal to each other because f is Riemann integrable, alpha prime is Riemann integrable, so f times alpha prime must be Riemann integrable. And so hence, since f and alpha prime are Riemann integrable, what do we have? Then we have that the upper integral of f d alpha, which is equal to the upper Riemann integral of f times alpha prime, which by the integrability must be equal to the lower Riemann integral of f times alpha prime, which we've shown is equal to the lower Riemann-Stieltjes integral of f d alpha. But now, what have I shown? Now I've shown that the upper and lower Riemann-Stieltjes integrals of f d alpha are equal to each other. So what does that tell me? That tells me that f is Riemann-Stieltjes integrable with respect to alpha, and the value of that integral must be equal to the common value of this, which is just the Riemann integral of f times alpha prime. And that completes the proof. Now again, this proof is very detailed and very nuanced, right? Each line requires a bit of thought. So again, I encourage you to go back and sort of think about big picture what's happening, and then try to break it down maybe into even sort of smaller chunks, and then eventually be able to understand the proof line by line. If you run into difficulty with that, of course, you should always reach out. I'm happy to provide additional clarification on any of the steps that make up this proof. But again, also it's a valuable exercise, at least for a bit, to try and work through it on your own and understand what's going on. In the next video, we will continue looking at Riemann-Stieltjes integration, in particular looking at some other properties that hold, maybe that don't necessarily relate it to the Riemann integral, but are important properties that we can use to calculate the value of Riemann-Stieltjes integrals when this theorem may fail, right? So I'll remind you that this theorem only applies when alpha is differentiable, which, as we discussed at the outset, is a very restrictive condition, actually. So we'll still want some additional theorems that help us compute Riemann-Stieltjes integrals in the case that alpha is not differentiable.